In this video, we're going to take a look at another curve sketching example. So we'll jump right into it. F of x is equal to 2x to the 5/3 minus 5x to the 4/3. We are going to first look for our x-intercepts. How do we find those x-intercepts? Well, we set our function equal to 0. So we could factor out x to the 4/3. So we'd have 2x to the 1/3 minus 5. Setting that equal to 0. So when x to the 4/3 is equal to 0, we get x equals 0. And for the other piece, when we set this piece equal to 0, we'll get x to the 1/3 is equal to 5/2. So x is equal to 5/2 cubed, which is 125 over 8, which is 15.625. So those are the x-intercepts at 0 and 15.625. The y-intercepts, we just plug in 0 for the x value. So y equals 0 is the y-intercept. Next, we want to think about our domain. So are there any places where we have problems with this function? Both of these are odd roots, and you can take odd roots of negative values, and so our domain has no issues. So our domain is all real numbers. Our third step, not the fourth, is discontinuity. Because our domain is all real numbers, there is no discontinuity. Great. Now let's think about intervals of increasing and decreasing. So let's look at our derivative. So our derivative is going to be 10/3 x to the 2/3 minus 20/3 x to the 1/3. Which we could factor out of that 10/3 x to the 1/3. If we factor that out, we will be left with x to the 1/3 minus 2. Setting this equal to 0, would tell us that x is 0, or x is 2 cubed, which is 8. And so that if we were to set this piece equal to 0, x to the 1/3 equals 2, so x is equal to 8. And so our sign chart, we are going to go from negative infinity to 0. We'll go from 0 to 8, and then from 8 to infinity. This is a sign chart for our first derivative. Plug in something smaller than 0, so some negative value. If we plug in a negative value, we will end up right here. We'll have a negative times a negative, which is positive. Plug in something between 0 and 8, so like 2. We'll have a positive times So 2 to the 1/3 minus 2, that would be a negative value. So positive times a negative is negative. Plug in something larger than 8, and we'll have a positive times a positive. And so, what does this tell us about our function? Well, f is increasing on the interval from negative infinity to 0, along with 8 to infinity. That should say infinity over here. And f is decreasing on the interval from 0 to 8. So we are going to have a maximum at least a local maximum, at 0, 0, and a minimum at 8, comma, negative 16. Okay, so how do we know that? Well, it changes from increasing to decreasing at 0. When we plug 0 into the original function, we get 0. So that's our maximum. It changes from increasing to decreasing there. At 8, it changes from decreasing to increasing, so we must be at a minimum. Plugging 8 into the original function, we get an output of negative 16. Good. So now let's find our inflection points. So to find our inflection points, recall our first derivative was 10/3 x to the 2/3 minus 20/3 x to the 1/3. So our second derivative is 20/9 x to the negative 1/3 minus 20/9 x to the negative 2/3. We could factor out a 20/9 x to the negative 2/3. And if we do that, left with x to the 1/3 minus 1. Setting it equal to 0, so f double prime equals 0 when x is 1, and f double prime does not exist when x is 0. Right. So this is in a denominator because it has a negative power. So our sign chart for the second derivative, we're going to go from negative infinity up to 0, then we'll go from 0 to 1, and then we'll go from 1 to infinity. Plug in a value that is negative, so negative 1, negative 10, whatever value you want to plug in. Plugging in a negative here, you'll get a negative. Plugging in a negative here, we will also get a negative. So a negative times a negative is a positive. So that is positive there. I was wrong. I said this was negative. Why is this not negative? Well, because that 2 is squaring it. So that's a positive. You got to be careful. So this will have a positive value. No matter the value of x, you're going to get a positive value there. And then that part will be negative. So we have that negative times that positive gives us negative. Plug in something between 0 and 1. We are still negative here, and the other piece is still positive. Beyond 1, we will have a positive. So we are concave down. F is concave down on negative infinity to 0 along with 0 to 1, and F is concave up on 1 to infinity. We're going to have an inflection point at when our x value is 1, our y value is going to be -3. So an inflection point at 1, -3. I'm plugging that x value of 1 into the original function. So that's our inflection point. Now we need to look at our end behavior. So the limit as x heads towards infinity as x gets really, really large, this is getting really, really large, right? And as x heads towards negative infinity, two x to the 5/3 minus 5x to the 4/3. As we head towards negative infinity, we also get a infinity, but a negative infinity here. So that's what we end up with. And so let's graph this thing. So our graph is going to look like this. So at 0, 0, we had an intercept. Somewhere past 15, we had an intercept. When our x value was 1, we had an inflection point at 1, -3. And somewhere here at 8, we had this minimum at 8, -16. And we were increasing up to this point. We hit a maximum, increasing concave down, continue concave down, but start decreasing. This was our inflection point, so we're going to change from concave down to concave up, but still decreasing. And then we stay concave up and start increasing again. So we have something that looks kind of like that. And so we were concave down up to this point here, and concave up past that. We were increasing up to that point, and then we were decreasing up till 8, and then we were increasing again. And that is our graph. So come on back, and we will look at yet another example. We will see you then.